What's up, folks? Coach Bach here. We are talking about the force velocity curve of muscle. This is a topic of much controversy and much confusion in the strength and conditioning world. So, we're going to see if we can bring a little clarity to the situation. All right. So, this curve represents the maximum possible force that a muscle or a muscle fiber can produce across a range of contraction velocities. All right. The left side of the curve represents a muscle being forced to lengthen. So that is considered negative velocity. That's called eccentric muscle action. Okay. The right side of the curve is the muscle shortening. It's called concentric muscle action. And that's considered positive velocity. So you can see the general trend is at lower velocities, your muscles can produce greater force, and at higher velocities, they can produce lesser force. All right, that general relationship is kind of the key thing to understand here. Now, where does the relationship come from? What's the mechanism behind it? That, as best as we can tell, comes from some variables in the myosin-actin cross-bridge formation. Okay, so the rate at which you can form the cross bridges, the rate at which you can detach them, how many can you form while the filaments are sliding past each other at different velocities, right? That's a variable. And then also how much force you get from each cross bridge at different velocities is a variable. So bunch of things that go into that. I wouldn't say we have that fully understood. It's a pretty complicated topic. But yeah, something in that realm of myosin-actin cross-bridge formation is, as far as we can tell, where this comes from. Now, typically in strength and conditioning education, you're shown this curve as kind of the end product of a whole bunch of research, and you're just supposed to know what it looks like. It's just kind of presented as a fact, but yeah, there's actually a long history there, and there's also a lot of variables that affect this. Things like temperature and fatigue and all types of stuff. So it is not as simple a topic as just here's one graph. This is true. There is a great research review that shows the whole history of the research on this curve, and here's the title there. And this is a beast of a paper for those of you who want to get into the nitty gritty of the research and maybe understand some of these things at a deeper level. That's an excellent paper. It's got over 200 citations in it. Yeah, really helpful, really informative. Shout out to the authors on that one. All right, so the force velocity curve is a very important property of muscle. It's helpful for understanding the stresses on our body during different movements, understanding the stimulus that we get from different types of training, right? But we have to be cautious in our application of the curve to exercises or to full body movements, because there's some obvious differences between full body exercises and testing in a lab, right? Like the research, a lot of it involves isolating a single muscle fiber and artificially activating it with electricity, and then testing it with different loads or at different controlled velocities by some type of machine or apparatus. And so there's obviously a lot of differences between that and you running a sprint or doing a squat or something. Okay. Now there is human full muscle testing and even full body movements in the research for this, and it is consistent. Okay. So if you have a person on like a leg extension machine, for example, and you test them at different velocities, the results are the same. Same thing even with full body movements. But again, there's differences between full body movements and isokinetic testing. Now, I've even heard it said that the force velocity curve does not apply to full body movements. And that, I know where people are coming from when they say that, because yeah, isokinetic testing in a lab or isolating a single muscle fiber in a lab is not the same thing as, going out and playing a sport. But I think it's an overstatement to say it does not apply. It's a property of muscle that doesn't change with different movements. Okay. And so I think it applies. We just have to be thoughtful and detail-oriented in our application. So we are going to attempt some application to full body movements. Okay? First thing we have to remember, the curve represents maximum possible force at a given velocity. Okay? It does not represent the force of all muscle action at a given velocity. Okay, so for example, if I think about the quads and I'm standing up off the couch, the tension in my quads does not show up on the force velocity curve because I'm not generating maximum possible tension when I stand up off the couch, right? So the tension would not be anywhere on this curve. It'd be like somewhere down here. All right. So it's only maximum possible tension. So it's only context in which you have high effort level in like a prime mover. Okay. You don't just apply this to any muscle anytime. Another thing to keep in mind is that the activation in a particular muscle is going to vary throughout a movement, right? It's not always maximal just because, the effort is high in general. Like let's say I'm sprinting at maximum effort. That doesn't mean that at all points during the sprint, my hip flexors are being activated maximally. Okay, activation can vary. So that's another thing to keep in mind. And then also, velocity changes during the movement. So again, it's not isokinetic testing. You're not stuck at one velocity. In a lot of cases, you're going to be moving and operating at different points on this curve during even a brief period in a dynamic movement can be changing velocity pretty fast. All right, so a lot of stuff to keep in mind. But let's talk through a hack squat and the quads. Okay, so we're picking a hack squat because we know we're loading the quads, we know they're a prime mover, and so assuming maximum effort on behalf of the lifter, we can try to apply the force velocity curve to that movement. So let's say we're using a medium weight, and let's say we are going down slowly. So on the descent, where are we at on the curve? Trick question. You're not on the curve. Why? Because on the descent with a medium weight going down slowly, you are not generating maximum force, right? You are not putting maximum effort. You are allowing the weight to go down. Okay? So you're doing a slow eccentric with a medium weight. Your force, your muscle tension is not up here. Okay, it's going to be floating down here somewhere. Okay, slow eccentric enthusiasts, sorry about it. Okay, the force is low there. If you're moving at a steady rate, that just means you're matching gravity. Okay, not generating high force in that context. So the descent is down here somewhere. Okay, now when you stop the weight and change directions, we're going to assume that you're putting maximum effort in. Okay, we're going to assume that you're generating as much activation of the quads as you can. In that moment, now you're going to get onto the curve. Okay, and so if you're going down slow with a medium weight, once you turn on that maximum effort, it's probably not going to force your muscles to lengthen much more at that point, but you probably have, a brief moment where you are on this slow eccentric part of the curve. Okay, so in that moment of reversal, you are going to be on that eccentric side, generating some pretty high force. Then as you stop the weight and you change directions and your muscles start to shorten, you're going to move from there onto the concentric side. Assuming your effort remains maximal, you are going to stay on the curve because it's high effort, and you're going to continue to accelerate, get a little faster, and so you're going to move down the curve a little bit. Okay, I don't know exactly how far. Obviously, it depends on how heavy the weight is, how fast you move it, whatever. But yes, you're going to be starting on the slow eccentric side and moving to the slow concentric side in a hack squat. Okay, so I think application of the curve is possible. We are making some assumptions there, but yeah, I think this is a reasonable application of the curve to a full body movement. All right, then let's talk about a seated jump where you start out sitting on a box or a bench, right? So in that case, you're going to be starting out at isometric. So you're starting right on the middle of the curve, and then you are going to not go to the eccentric side, but just fly down the concentric side to a pretty high velocity as you accelerate off that bench and you reach the height of your jump. Okay, so starting in the middle and then flying down the curve or like surfing the curve to a pretty fast velocity at the top of that jump. Now there might be a little more complication in there as far as the muscles maybe shorten and maybe the tendon lengthens a little bit, and then as the tendon shortens, maybe the muscles aren't having to shorten as fast. Okay, so there might be a little muscle tendon mechanics complication in there, but still we're talking about starting in the middle and moving to the concentric side. All right, so again, I think it's possible to apply the curve to a full body movement. Now, notice how those muscle tendon unit mechanics maybe get a little more complicated with an explosive movement. Yes, and that brings us to the point that ballistic movements, okay, so sprinting, plyometrics, like approach jumping, that type of stuff, they get complicated, okay? So let's look at a standing vertical jump. You may look at that and see this big range of motion happening. Let's keep thinking about the quads here. All right, so you see this big range of motion at the knees. And so you might think, okay, the muscles are going from fast lengthening all the way to fast shortening. All right, and that is true. And so you might think on the force velocity curve that you're starting all the way over here and you're flying all the way over here in the quads. However, you got to remember that while you're dropping down for that standing vert, you're not generating maximum possible force, right? So that fastest lengthening of the quads, you are not going to be on the curve during that time because you're not generating maximum force. You're allowing your body to accelerate downwards. Now, once you do turn on that maximum effort and activate your quads, there is still some lengthening of the muscle tendon unit, okay? But it's not real clear how much the quad muscles themselves would actually lengthen. They might actually stiffen pretty quick and then the tendon would do the lengthening. So there's this body of research, again, that shows that during ballistic movements, the muscle might actually stay closer to the middle with its shortening velocities. And then the fast lengthening and fast shortening is done more so by the tendon. So here's a good study that addresses this, and it cites a bunch of other studies that looked into this topic. So here's some graphs from that study, and they found that in the gastrocnemius muscle, so the calf, the muscle fascicles did not lengthen during a counter movement jump or during a drop jump. So the muscle tendon unit as a whole did lengthen a little bit, at least in the drop jump, but the fascicles, the muscle fascicles did not. They actually slowly shortened the entire time. So that kind of clues us into how the muscle tendon unit might function during ballistic movements. However, a big limitation in that study and in, as far as I could tell, like almost every study that it's cited, is that they use the gastroc, which is a biarticulate muscle. It crosses the back of the knee. And so if your knees are bending, then the muscle is shortening on that end. And so even if it's lengthening on the ankle end, then the muscle itself might stay more isometric. So honestly, I don't think the gastroc is the right muscle to examine to answer this question. We really need the soleus specifically from the calf, or like the vastus muscles from the quads. That would be more insightful. So point being, if we consider the quads in a standing vert, you drop down fast, you have momentum, you turn on that maximum effort. It's not clear how far to the left on the force velocity curve your quads would operate in that moment. Personally, I think, they're definitely on the left side of the curve, and I would bet that there's a moment at least of fast lengthening. So we'll just say maybe they're starting like here, okay? But then definitely from that point, they're going to stiffen. So you're gonna move to the isometric part of the curve, the middle, and then on the shortening, again, the tendon is probably doing the fastest shortening, but the muscles are definitely shortening too. And so you're moving, into this concentric side of the curve. Exactly how far down it would go, I'm not sure. Yeah, so some of the details here were a little hazy on, I would say. Okay, now another good example is sprinting and the hamstrings. So there's this question of eccentric action of the hamstrings during the late swing phase, right? So let me just try to make a little person here. So that's spine, there's head. Okay, so then we got legs. All right, so there's a moment in the sprint cycle where, well, it varies between people, of course, but generally we have a moment that looks kind of like a butt kick, right? It might be a little different position on different people. And then we have a moment where the knee is lifted and the shin kind of flies out. And so then, they stop maybe somewhere around here or something. And then from there, the whole leg goes down and back. So definitely from this moment to that moment, the hamstrings lengthen a lot. Okay. But just like we talked about before with the activation, during the early swing phase, you're not activating your hamstrings at a high amount, or at least you shouldn't be. It's the late swing phase when you're kind of stopping the lower leg from flying forward. That's where you really get maximum activation of the hamstrings. And so in that moment, how much are the hamstrings being forced to lengthen? And, people have kind of made some theories about, no, it's really more isometric at that moment. And maybe, maybe it's just a little bit of eccentric. I'm not sure. But so again, you kind of have this question of, even though the muscle tendon unit is lengthening, how much is the muscle itself lengthening, and how much is it the tendons? The hamstrings don't have a long tendon like the Achilles or the patellar tendon, but still, there's a question there about the muscle tendon unit mechanics there. But so yeah, we have a very high force isometric / eccentric moment for the hamstrings in sprinting, and that's why obviously hamstring injuries happen, and that's why we try to strengthen the hamstrings a lot to prevent those injuries. Now, the key thing I want to point out is, regardless of how eccentric that muscle action is, whether we're talking about the hamstrings in sprinting, or the calf in sprinting when you hit the ground, or the quads in the vertical jump, or whatever, regardless of how far out on the curve that action is, we know that the peak forces in the muscle tendon unit get really, really high in dynamic movements. Okay, so it's not easy to measure those forces. It takes a lot of data and analysis to create estimates. But if you look into that research, you see numbers like 12 times body weight in the Achilles, right? Or 8 times body weight in the quads, or 10 times body weight in the quads at peak force during some type of jump, or the hamstrings in sprinting, like 8 times body weight peak force. And so there's definitely some really forceful stuff going on during these dynamic movements, and that occurs probably partially due to the contractile element of the muscle operating like on this side of the curve, generating a lot of force in that moment, but then also because of the connective tissue, right? So like the connective tissue framework of the muscle, we call that the parallel elastic component in anatomy and physiology. There's probably a lot of tension happening there, and then of course both of those things are being transmitted to the tendon, and so we get really high tendon force in those moments, regardless of exactly where the sarcomeres are at on this curve. Okay, so I hope that gives some understanding of the curve, and also how we can apply it to full body movements, even if it's kind of complicated and a little bit gray at some times. This is definitely knowledge you want to have, you want to understand, and you want to use to understand the stresses on the body during different movements. Now we got to talk about this. So this is a pretty common practice in strength and conditioning. It's assigning movements to different areas on the force velocity curve. Typically just the concentric side of it is what people use. Now, after what we just went through, I hope you can understand that putting movements on one part of the curve like this is drastically oversimplified and reductionist. In reality, any particular movement, even in one muscle, is typically going to be moving to different areas of the curve and maybe even covering a broad range of the curve. And then certainly if you consider different muscles, you're going to have actions all over this curve. And so, yeah, it's definitely, without providing any context or details, it's kind of silly to just put a movement on one part of the curve. That being said, I've always understood this to just be referring to the peak concentric velocity of the prime movers. And so I've never really had a problem with that. People just they don't typically provide that detail of how they're defining those movements. But I've never really had a problem with this. It's just oversimplified. Now, some people really have a problem with this, and they will, criticize this practice. And it's somewhat valid, but I've seen people make the statement that the force velocity curve is BS. And I'm like, well, no, it's a property of muscle. The curve isn't BS. Maybe the application of it is BS, or maybe putting those exercises on there like that is BS. But the curve is not BS. And then again, I've seen this, the force velocity curve does not apply to full body movements. And yeah, I know where they're coming from. I don't really agree. But what I really don't like is they'll make that statement, then they'll point out the ground forces in a sprint or a plyometric, and they'll be like, look, these movements are high force and high velocity, and so the force velocity curve doesn't apply. But the force velocity curve doesn't refer to ground force at all. It refers to muscle tension, muscular force, and so it makes no sense to bring up ground force in your critique of this practice of putting movements on the curve. So, I just got beef all over the place there. But yeah, I would say assigning these exercises to parts of the curve isn't real useful, probably doesn't make a whole lot of sense. But if you specifically say that, the peak concentric velocities in these exercises, then maybe it's somewhat accurate. When people do this, they're often using it to support this concept of surfing the curve with different exercises and saying you need to do exercises all along the concentric part of the curve. But hopefully from what we've gone through today, you can see that, even in one muscle, on one exercise, you might be surfing a pretty big portion of the curve. So for me, you say, yeah, I have to surf the curve. And I'm like, okay, well, I did sprinting. And so there it was surfed, right? I did a dunk session. And so, yep, surfed the whole thing with that, right? I still, really, really skeptical of this claim that we have to, do sprinting, jumping, then loaded jumps, then slightly heavier loaded jumps, and then cleans, and then like fast squats, and then heavy squats to hit like, an exercise that sort of focuses on each area of the curve. I just kind of reject that philosophy. Now, obviously your training is going to have variety in it. And so you're probably going to do some explosive lifting. You're probably going to do some heavier lifting. And so you're probably going to surf the curve to some degree. But yeah, the idea that we have to like hit every part of it with specific exercises, not a believer in that. So that was a long video. Hopefully it was informative. Hopefully you guys liked it. Maybe I made a couple new friends, maybe a couple new enemies. Feel free to argue with me about it. Have a good one.